Guys, very good afternoon to you all. So what I'm going to discuss today is about the quantum AI, the road ahead for AI-powered testing. Very important in the sense that I'm not going to, though I shall start with the current state of the art about the AI, but primarily I shall take you to the road ahead in the sense that how the AI-powered testing would look like with the amalgamation of quantum computing with the AI. So that's precisely the uh, focus area where I shall take you to. My introduction or my background has been discussed by Krunal. So I have got the first 10 years of my experience was into academics. I used to teach in the leading B schools of the country, primarily of Delhi NCR, teaching subjects like statistics, analytics, AI. Then moved to industry, worked with multiple companies. Analytics and AI. So what we have seen or what we are envisioning is that a paradigm shift is going to take place in the technology space, in the sense that the current state, what we are currently having, is about the intelligent test automation. Now, what do we mean by intelligent test automation is that by the application of AI, by the application of machine learning, the automation of software testing, which is nothing new. We are quite familiar of what kind of work, what kind of tasks are being automated, and how AI is managing those tasks. Now, the thing or the vision that we are having is that the road ahead, how quantum computing led or quantum computing powered AI will take the entire software testing and how they are going to benefit us. So as you can see here in the diagram that how the time factor squeezes or reduces with the passage of or with the advent of the technology. So from years it goes to months and then weeks and then finally into days or minutes. That's what is happening when you are going to apply these advanced techniques like quantum AI. So before going to quantum computing or quantum AI, let's see that what's the current state, what's the current state of the art of the AI test automation. So one very important part is that the design and the runtime, they are going completely hand in hand these days. So not that that design used to take, that's what we used to have a decade back. Like design used to have then the modeling, programming, validation, verification, requirements engineering. And then once that is done, then we go to the runtime. It doesn't happen like that. It works in a kind of complete loop. Like with this designing part is over, the deployment is done, and then the runtime is being done with the self-adaptation, awareness monitoring, and then comes the feedback in an automated way, and this cycle goes on for the constant development, constant integration, or the continuous integration. And how the AI gets applied to software testing these days with primarily three areas. One is the first one is the AI driven testing, in the sense that how the AI test gets developed to test the software. Then there is devising methods to test the AI system. It is the testing the AI system. The second way. The first one is the developing the AI tools to test the software. If you can develop some algorithms to test the software, the algorithm should be AI driven. The second one is the devising the methods to test the AI systems which are already in AI, how to test or how to devise the methods to test them. And the third part is the most interesting or the critical, where the self-testing or the self-healing takes place. So the entire cycle of testing, whatever is the feedback is taking place, and it goes in a loop. So that's the self-testing, the self-healing part. And typically what happens when the AI gets applied to software testing, it elastically scale functional, load, and performance tests, seamless integration with the existing CI/CD process, AI test cases the update automatically, intelligent testing, RCA being done in an automated way, and there are seamless integrations with all the third parties and the major components. It can talk to the entire ecosystem in a seamless way. So that's the power of AI that gives to software testing. And what are the key approaches for the AI-driven testing? The first one is the differential testing, in the sense that comparing applications or the various version of our builds, classifying the differences, learning from feedback on the classification. That's the differential testing. You segregate it and then test. The second one is the visual testing, leveraging the image-based learning and screen comparisons to test the look and feel of an applications. So you test it based on visual, and of course, goes without saying that we apply all the deep learning techniques in this visual testing, like the CNN, RCNN, whatever are all the image generation techniques or image classification techniques. We use all those techniques in the visual testing. Then we have got the declarative testing, specifying the intent of a test in a natural or domain-specific language, and having the system figure out how to carry out the test. That's the declarative part. And finally, that we discussed is the self-healing automation. So auto-correcting element section in test where the UI changes. So it changes or corrects itself in an automated way. So that's the four main genres or four main divisions of the AI-driven test. And of course, the benefits are it is in most of the cases codeless because it is all automated. It brings a lot of simplicity to the process. It is scalable. It can accommodate more amount of data, and of course the time reduces. Of course, the cost also reduces when the time reduces. Then it is more accurate. There is no human error as such. Productivity increases multifold, and it has got extreme flexibility. So that's the benefits of the AI power. So as I mentioned that this, what I have said just now is nothing new. I shouldn't say nothing new in the, yeah, it's all new, I understand. But then these things are kind of, is an ongoing process, it is going on. It is not something in the future, it is the present state. So from that perspective, it's not new. It is yesterday and today. Now, what I'm going to discuss now is about what is the road ahead. So this path is not now widely available. It is primarily to the testing phase, and of course, quantum computing has advanced. Quantum AI is also following, but the application of quantum AI in the software testing is the road ahead. That's not that prevalent what we are seeing in this AI-driven testing approaches or the AI-driven software other methods. So what is happening into the quantum AI part? But before jumping straight to quantum AI, it's possible that many of you are not very aware or may have a very high level knowledge about quantum computing, though it's the detailed subject altogether. But I shall, give you some very, specific areas or specific cues so that you can understand that what quantum computing is, and you can will appreciate at least this presentation in the light of what I'm going to discuss. So first difference I would say between classical computing and quantum computing is that classical computing works in binary nature. That means it is having a kind of 0 and 1. We all know it. We all know it from our childhood. But quantum computing, smashes that idea and says that, hey man, it's not about either 0 or 1. You can have both simultaneously. You can have both 0 and 1 simultaneously. So that's the beauty. That's the beauty of quantum computing. So that's what I explained here in that image, that 0 and 1 are the classical bits, where in the qubit you can have 0 and 1 all together. So calculates with transistors, it is the classical computing part with 0 or 1, whereas with the qubits, it can represent 0 and 1 at the same time. And naturally, if that happens, if that takes place, then the power increases exponentially in proportion to the number of qubits. But whereas here, it is a kind of 1:1 relationship. It's a kind of very straight line. And now some downside in the, I shouldn't use the word downside, there are some conditions required, that it has to require an ultra cold temperature because they have got high error rates. System needs to be kept cold, whereas classical computers, the error rates are low and can be at the room temperature. And this is well suited for the tasks like optimization problems, data analysis, simulation, which are far more complex, where the solution is not that straightforward. Quantum computing can generate multiple results, compare, and come up with the right results at a very small amount of time. That's the beauty. That's the beauty. Even our classical computer can do the same thing. I'm not saying it cannot do quantum optimization or data analysis, but then the entire process is much more longer, and with the process, the time and the cost increases. So that's the beauty of quantum computing. I hope you got some idea, some clarity you got. Of course, and you are going to have more clarity once we proceed. So as I discussed that how a quantum computer works, in the classical base you are having this OR part is very important. That's 0 or 1. That's how a binary system work. Whereas in a qubit, it's a kind of superposition. That's the kind of term we use, which means nothing but overlay of different states. So you have got multiple states running together. As you can see here, it is not just one state 0 or 1. You have having multiple this orbit, this orbit, this orbit. So in that way, multiple orbits are running together at the same time. So what is the beauty? What is the outcome of what are the advantages of such kind of superposition? First is that parallel arithmetic operations possible. So that's huge or massive advantage. And exponential multiplication per qubit and massive amounts of data can be handled in plausible time. So that's how a quantum computer works. So yeah, that's how is quantum different. So that's one thing I'm continuously hammering on is that the classical state is 0 1, what is the quantum state, as you can see here. How many states can exist? It is not just two or three things parallelly. It can be with n qubits. We can have 2 to the power n paths. So that many amount of operations can go on simultaneously. So that's the power. That's the power. Quantum computing is more powerful than the classical computers. The other thing is the entanglement. So the states of entangled qubits cannot be described independently of each other. So that's again a very interesting phenomenon. Though we will discuss that, of course, we apply. So this is a phenomenon of quantum computing, but in the quantum AI, we apply the complex neural networks, complex algorithms to unentangle rather these states of entangled qubits, which of course is still going on. Massive research is going on. We apply the different forms of recurrent neural network, even the reinforcement learning in the quantum computing to unentangle and then get some values which we can look and feel. Otherwise things get pretty black box. So MLAI already is in a black box, but if this happens, that got further black box. So we know we are figuring out how to illuminate that black box. So why quantum will be quicker? For the simple reason that your PC performs calculations using bits, right? You need information in either 0 or 1, off or on. Whereas that's how a traditional computer works, right? One by one until it finds the right solution. This leads to this leads to this. That's the way it proceeds. Whereas a qubit or a quantum bit can exist as 0 or 1 or both simultaneously. This state is known as superposition. So adding more qubits therefore increases the number of states that can be represented exponentially. So as you can see here, so it is not a kind of this linear fashion. This is a kind of course, it moves linearly, but there are a lot of simultaneous activities going on at each stage before it gives the results. So that's called the superposition. One of the properties of a quantum computer that enables it to work faster than many possibilities at once. So it is having the number of possibilities at every go. So sorting through sets of probable outcomes that converts on the correct answer. And then so now we have got some clarity, I'm sure, by last 10-15 minutes whatever we discussed about quantum computing, we got some clarity about what quantum computing is and how it is beneficial, how it is better than the classical computer. So now we are slowly moving into the realm of quantum AI. So what is quantum AI? Is the use of quantum computing for the computation of ML algorithms. So what is ML algorithms? Perhaps that is something well known to majority of the audience, right? Machine learning means typically just a couple of minutes I can throw some light if it is not known to you. Typically, what happens in the machine learning algorithms or how it is different from the traditional statistical algorithms is that we create a kind of feedback loop. Suppose traditional analytics or traditional statistics can be a regression problem. Now that regression problem, a simple equation y equals to a plus b1 x1 plus b2 x2 plus e has got no feedback loop into it. So there is always an error component associated there, right? But in the ML algorithm, what we do is that we create a kind of feedback loop, and we do a lot of iterations, a lot of training in that language. We call it a kind of training. By doing a kind of training, we keep reducing by doing a lot of iterations, we keep reducing the error component. So the predictability power of our algorithms improves. I hope I'm clear. If you have a background in the statistics or ML. So now it happens is that thanks to the computational advantage of the quantum computing, quantum AI can help achieve results that are not possible to achieve with classical computers. So nowadays, if we get a project, it takes a good amount of every iteration we do almost to get kind of very high standards of predictable powers and 95% accuracy of the model. If we need to generate that, we do easily some 500 iterations or so. Easily, it happens. It goes to that level. But then this training part of the model or testing, these things take a good amount of time, because every time we see, note what is the error, and then we tweak the model and fine tune some hyperparameters and then let it happen. So that's a kind of linear process that I've shown in the few slides back. But then this entire 500 iterations can go all in a simultaneously. Can you imagine? That's the beauty. That's what the quantum AI comes. That's how it gives power to the traditional ML algorithms. I hope I'm clear. If not, then I can again take this aspect in the quick Q&A session. So that is exactly what I was discussing, that how does quantum AI work. So now a kind of step-by-step procedure. So that's a kind of philosophically that how it works, but now practically how it works. So first step that we do is that convert quantum data to the quantum data set. So these two things are not similar. So that's why quantum data can be represented as a multidimensional array of numbers, which is called the quantum tensors. So TensorFlow process these tensors in order to represent a create data set for further use. So that's how we consider it. And then we choose the quantum neural network models. Again, a very important, not the classical computer neural network models. So we require the quantum NN models, and based on the knowledge of the quantum data structure, quantum NN models are selected. Aim is to perform quantum processing in order to extract information hidden in that entangled state. If you remember, I was discussing this thing when I was discussing the entanglement. We use the sophisticated quantum NN models to unentangle it. So yeah, maybe some deep reinforcement learning or the deep even the recurrent neural network we can use. So that we have to sometimes we use even hybrid models. That's again another beauty. Maybe I shall throw some light if time permits. To hybrid in the sense that we mix and combine a few of the sophisticated deep neural network models and then use it for the quantum. Yeah, so that's kind of a lot of creativity work. It's not that mechanical. That's where the data scientists come, because it's not whether you can write a code in R or Python. It is all about how creatively you can create a dish. I would say, if I can give an analogy, out of the several ingredients that are given to you. So that requires a lot of creativity. And then sample average in the sense that measurement of the quantum states extracts classical information in the form of samples of classical distribution. So values are obtained from the quantum state itself, and the TensorFlow quantum provides the methods for averaging over several runs, providing in these two states. And finally, evaluate a classical neural network model. So since quantum data is now converted to classical data, then deep learning techniques are used to learn the correlation between the data. So yeah, now we are again, coming back to the classical state. So that's how it happens. Like prepare quantum data set, evaluate quantum model, sample or average, and finally coming back to the classical model. So that's how the quantum AI works. So what are the typical challenges that we face in the quantum powered AI? So the first is the quantum or the feedback loop. Like replace the feedback loop around training entirely with a quantum algorithm. So again, you have to be very clear. As I mentioned, that training means training the data sets the way we traditionally do in the ML algorithm. Those traditional ML algorithms, how creatively we can replace that with the more creative quantum algorithm. That's the greatest challenge, I would say, because that would actually reduces the time and cost, and the most important part is that increase the productivity. And the second challenge is that training data provide means to process large amount of data on quantum computers. So means to process is not only about the hardware, by the way. It is all about how you can creatively bring or hybridize that multiple algorithms, combine the multiple algorithms to make the large amount of data gets processed in the quantum computer. Then the interfaces in the sense that provide a standardized interface that allow for dynamic combination of QAI components for experts of different fields to collaborate. So interfaces on this quantum computer are again a very big challenge, and the real reason keep track of the source of the observed improvement. Even in the classical ML, it is so difficult to keep track of every bits and pieces of the improvement in the model. When we are doing in a more black box situation of a quantum AI, that gets to know further challenge. So these are the key challenges that we face. Of course, this is the kind of what kind of algorithms generally go into this kind of quantum environment situation is typically the Grover's. There are multiple algorithms actually. I've just taken one most popular algorithm, I would say. The Grover's algorithm is the such algorithm, and that shows that how in an unsorted database, how it can reduces the time to O to the power root to n, and then compared to the ON steps by a classical computer. So that is the kind of example of a quadratic speed up in the competition time. So that's something phenomenal, I would say. Now, what are the benefits of quantum computing powered software testing? The first is the time complexity as the advantage of speed over its classical counterpart. Uh, in an unsorted database, as we have discussed, the Grover, it had time which is quadratically faster than a classical computer does to complete the same task. That's the time complexity or time advantage we're having. The cost advantage that we are having is that half the cost of developing complex software is on the verification validation VV part, and the cost is increasing. So next gen software, the VV part will require new computing paradigm. So if the majority of the cost goes in the verification and validation part, so we have to improve that part. We have to augment that part in a phenomenal way, and that can only be possible by bringing the quantum computing, and not the traditional AI can actually match. So and match the more advanced software that we are having these days. So what are the typical bug types in software testing, the quantum software testing? So the first one, if I can say the incorrect quantum initial values, so you have to check the assertions. Of course, what is assertion? I'm coming to that part in more detailed way in subsequent slides. Assertion checks for the classical superposition conditions, incorrect operations and transformation. Assertion checks for unit testing. For the incorrect composition of operations using, we do the assertion check for the classical intermediate states. For the incorrect composition of operation using recursion, we use the entangled intermediate states. For the composition of operations using mirroring, we use the product state post conditions. So for every bug type, we have a different strategy in place. That's something we are pretty familiar, and that is familiar in the sense that this part has already been discovered. So this part is done. So what is assertion part? It is again not only for the quantum software testing. It was there earlier as well. Typically, it is a statement about the expected behavior of a software component that must be verified during the execution. And the program defines an assertion to ensure a specific program state at the runtime. So how a program is expected to behave at every state of the runtime. So what kind of assertion library we are having in the quantum software? Typically, they assert probability, like use the robust statistical method to test the probability of observing qubit in each state, and then assert entangled, take two qubits as its occupants to test whether they are entangled or not. Assert equal, test the equality of two states in the quantum programs. Assert teleportate, test quantum teleportation as it is a significant protocol in the quantum realm. And assert transformed, like test the validity of any unitary transformation. So how this has been done in the quantum software testing? The first one is the quant-fuzz or the fuzz testing. So typically it defines some quantum sensitive information to evaluate the test inputs for quantum software and use a matrix generator. So you can randomly generate some input values, some numbers, and see that how the output goes. So that's the kind of to generate test cases with higher coverage. So that's the kind of fuzz testing you can do, which is called the quant-fuzz. Then there is Q-sharp check, a property-based testing approach for quantum software written in Q-sharp. We have got the functional testing, like initial system quantum test and set up in the initial status of qubits. And then similar to classical testing, quantum is executed. And finally, the test suite saves the obtained results to calculate the most probable result. We have got the white box testing, which looks at the internal structure, design, and coding. And finally, we have got the model-based testing, which uses the modeling language, for example, UML, to model the behavior of the quantum software. Final slide, what I'm going to discuss is about the quantum program debugging tactics. Now, debugging tactics are I would say these are also or present in the classical computer or classical software testing as well. But the same techniques of backtracking, looking at the root cause, follow every steps, and figuring out what lies the debugging part. That can be figured out in the quantum debugging as well. In the cause elimination, you can figure out a hypothesis or a root cause, and then test whether that cause holds true or not, and in the brute force where we figure out how what kind of debug or kind of bugs exist and how to debug it. And then assertion bus debugging, the classical assertion to the probability part that we have discussed here, like through a statistical method to test the probability of observing a qubit in each state. We can figure out if there is any bug exists there. Superposition assertion, as we have seen here, whether the entanglement exists or not. And we have got the entanglement assertion to figure out whether the qubits exist in the same state or not. So these are the typical assertion-based debugging methods. So I know it was too heavy to assimilate in this given time slot to me. If you have any question, you can ask me now. And I'm just on time, I can see.
Hi, guys, any questions?
Any question, guys?
So, Dr. Tuhin, it seems everybody is, probably still trying to break it down. Forget about digesting; it has to, it has to really put down. But fantastic presentation. I was just, I know I had a question till somebody else has a question. I thought I'll ask you. What's the time frame that you're looking at in which these things become commercially viable, and then you see the involvement of software testers coming into picture and so on?
Well. IBM, Microsoft, all the large companies currently are working heavily on it. Quantum computing, it is step by step. The way I have developed the is actually a step by step documentation of the process. So quantum computing was there for quite some time. Currently, people are thinking of how to leverage the power of quantum computing, quantum AI. So that's the second stage. We are in that stage currently. A lot of research, a lot of papers are currently been going on in 2021. Quantum AI in software testing is not yet there. If quantum AI goes very well for the next 2 years, so 2021 to 2023, then we can see this in around 2025. So that's the kind of vision I'm having. So 2 years, 3 years. That's how I'm.
Understood. Thank you so much. There are a few questions here. One question is related to demo. Is it possible to have a demo?
So yeah. So I have to really take a time machine, go to 2025 and give you a demo. You have to give the demo right away.
All right. So
I unfortunately don't have the time machine right away. Otherwise, I would love to.
So second question is, how do you migrate from traditional testing to this model?
See, philosophically, it won't differ. So migration challenge primarily come, as I discussed, is in the execution part. So debugging that is own different. Migration challenge could be in developing the right algorithm of the quantum AI to bring it to the software. How to migrate? Primarily, you have to have a quantum environment. That's the first part, which is itself a challenge. Then the quantum interface to have multiple experts give the right algorithms, right inputs to the process. Once the environment is ready, interface is ready, algorithms are ready, then only it is possible to migrate. Yeah, that's precisely it is. And of course, I hope that by that time, once that environment is ready, what I mean by environment is ready is that the algorithms will also, develop or improve, augment significantly. So that's the migration is not about the, of course, hardware is an important part to it, but it is not a kind of physical challenge. It's about the challenge of the how the subject, how the world body of knowledge improves, which is improving at a very fast pace, extremely fast pace. But that's where the main challenge lies.
Krunal, thank you so much, Dr. Tuhin. Krunal, do we have more time?
So we can take a question or two.
All right. So one question is related to need for specialized software for quantum computing. Is there a need for specialized software?
Yeah, absolutely, absolutely. I think QSILK is there, IBM, Microsoft, all the big companies are doing it. Yeah, absolutely, recently.
All right, thank you so much. Next question is, how does data security and data integrity done, considering a large amount of data is involved and processing is happening simultaneously?
See, you know the answer at the current state, correct? What is happening currently? Now, obviously, when with this amount of data, with this step-by-step process only, there are a lot of challenges. The challenge is not in the environment. To be very honest, I see the challenge is not in the quantum computing environment. Challenge is even before it reaches the quantum computing environment, security, privacy. These are the challenges that we are currently having. So I don't see that once it reaches the environment is such that it's very difficult to extract. At least with the current knowledge. Of course, that knowledge will also, enhance with time. But I don't see that's the kind of major challenge. The major challenge would be to secure the data where we are currently now. And that part is not secure. So we have to really work on making the data secure, even in the current state.
All right. Thank you. Understood. Thank you so much for your nice presentation.
My pleasure. My pleasure.
Thank you, Dr. Tuhin.
All right.